Hey everybody, so we're going to do a quick video here about learning objective 4-3, which is the law of conservation of momentum, and using the law of conservation of momentum to actually calculate values. So we're going to do kind of some old school math-based, algebra-based physics today, which should actually be pretty cool and set you up for some even more rewarding skills in our next session. Now, before we dive into this, we need to review the two types of energy that we're going to be talking about: gravitational potential energy and kinetic energy. So let's get to it. So on this page, you can see that we have our two guys here. We've got one weightlifter with the weight on the ground. This barbell has no gravitational potential energy because it is at no height. It is on ground level, or at least whatever we're calling ground level in this situation. Remember, gravitational potential energy is arbitrary, so it's whatever height you decide you're going to focus on. In this other situation over here, we've got our guy with the weight lifted above the ground, and you can see I've highlighted that height right here, and we're saying that he does have gravitational potential energy. What this brings us to is a reminder of the ingredients for gravitational potential energy. In order for an object to have gravitational potential energy, it must have mass, there must be some gravity, and it must be lifted to a height. Remember that in this case, m is the mass in kilograms, g is the gravitational constant on Earth, which is always an acceleration of 10 meters per second squared, and then h is going to be the height. Now we can look at this situation. This is talking about kinetic energy. So this runner over here, starting off in the blocks, has no kinetic energy as they are currently not moving. Whereas once they start moving and take off running, they're going to have kinetic energy because they're going to be moving. The faster they're moving, the more velocity, the more kinetic energy they will have. Which also brings us to a reminder of the equation for kinetic energy. The equation for kinetic energy is 1/2 of the mass times the velocity squared. Very important to realize that it is velocity that is squared in this equation, not mass and velocity. It's just the velocity that is squared. So velocity is very important in this equation because it does get squared. Whenever we're using these things moving forward in my notes, we're going to have gravitational potential energy be represented by the color green. We'll have kinetic energy be represented by the color blue. In all my previous notes, velocity was blue, and so we're just continuing with that same general idea. We're going to be looking at 3 example problems today. One is a cart or a roller coaster that is starting at rest from the very top of the highest hill on the roller coaster and is going to roll down 20 meters to the bottom of the hill. And we're going to try to figure out what is its velocity at that bottom. The mass of this roller coaster is a completely too light 100 kilograms, but we're going to go with it anyway. Our second example problem is going to be a snowboarder. She is cruising along at 10 meters per second at the bottom of this half pipe. She has a mass of 80 kilograms, and she's going to be launching up high into the air. We want to figure out how high she goes. At the very top of her flight, remember when you're flying up, you're following this kind of curved path. At the very top, you're going to have a moment, just like an instant of zero velocity. So that is what we're looking at up here, is that moment. And then off on the right, we're going to have an example of a wrecking ball that starts off at a velocity of 0 meters per second and swings down. At the bottom of its swing, it has a speed of, or velocity of 6 meters per second. It has a mass of 20 kilograms, and we're going to try to figure out what is the height. Now, the way we're going to do this is I am going to work on the first 2. So the roller coaster and the snowboarder, those are my responsibility. I'm going to fill those out and show you how those work. You are going to work on the wrecking ball. So you're going to complete that one. Now know that these problems are different. They follow the same steps, but the physics is significantly different between the problems. And so this is going to give you a chance to see how the physics and how the math are different in different applications. And I think that's going to help you understand it best over the long run. All right, so steps in an energy calculation. The very first step is to identify the before and after that you are focusing on. Okay, these are the two instants that you're going to compare. We don't think about the whole motion. We don't think about what happens before the before. We don't think about what happens after the after. We just focus on these two instants. In the case of the roller coaster, we have information about it while it is at the top of the ramp, and so we're going to call that before. We also have information at the bottom of the ramp, and we are going to call that the after. In the case of the snowboarder, we have information about the very bottom of the ramp. We're going to call that before, and we're going to call this the after. So notice that these are kind of mirror images of each other. We've got an object starting up high and going lower. We've got an object starting low and using its speed to go higher. So that is how we're flipping the situation. Take a second and think about how you're going to set your before and after. And I want you to circle them in red, just like I did, label the before with a B and the after with an A. Our next step is that we're going to write a conservation equation. A conservation equation uses the law of conservation of equation, the law of conservation of energy mathematically to kind of set up our own equation specifically for this situation. And so what we got to ask ourselves is what kind of energy is there in the before and what kind of energy is there in the after? In the case of the roller coaster, because the roller coaster is lifted up to a certain height, it is going to have gravitational potential energy at the beginning. Notice it also has no velocity, and so there is no kinetic energy. At the end, it has lost all of its height, and we're going to try to figure out what its velocity is. And so at the end, there is kinetic energy. So we've got GPE over here as the before. We've got kinetic energy at the end. Notice that there's an equal sign between those two. That's because according to the law of conservation of energy, the total energy before and the total energy after have to be equal all the time. Now notice that our situation here was kind of the opposite. We're trading kinetic energy for potential energy. And so I have the exact reverse of the previous equation. Take a second and think about your problem and write your own conservation equation over in this space on the notes. And I would also recommend that you use the color schemes. Color coding helps your brain remember stuff. So make sure kinetic energy is blue and make sure gravitational potential energy is green. Now that we've got that, we're going to go to the next step and we're going to start plugging in variables. So this is where we're going mentally all the way back up to the top. And wherever we see gravitational potential energy, we're going to plug in m times g times h. Wherever we see kinetic energy, we're going to plug in 1/2 mv squared. So notice I've done exactly that. I had GPE on the left, and now it's mgh. I had kinetic energy on the right, now it is 1/2 mv squared. Over here, because the snowboarder problem is the exact opposite of the roller coaster problem, I have the exact opposite equation. All right, go ahead and plug in the variables into your equation now. Remember, use the color code. Once you've got all of your information plugged in, it is now time to actually go back to the initial problem way up here and get all of your given information and plug it in. So in the before picture, this cart has a velocity of 0, a mass of 100, and a height of 20. So we're going to go back down, and we're going to see that mass is right here. It was 100, so we're going to plug that in. Height was 20, so we plugged that in. Gravitational constant is always the same as long as we're on Earth. It's always going to be 10. The mass is 100 again over here, even in the after picture, and we don't know what the velocity is. So guess what I did? I just left it as v squared. In my second example over here, you can see I did the same thing, except now the mass is different. So instead of my mass being 100, it is 80 in this problem. Also, I know the velocity, so I plugged in 10 into that space. What I don't know is the height, and so I just left that as an h, okay? So our plugging in is not always the same. We have to look at the information we're given and plug that in where it belongs. Take a second and plug in your information by looking all the way up at the very first picture to see what you know about your wrecking ball. After we've done that, it is time to do some algebra. And so here is my problem. I have all of this stuff. The first thing I'm going to do is I'm going to notice that I have a 100 on this side and a 100 on that side. So we're going to divide both sides of the equation by 100, which is actually going to cancel it out on both sides. If we flip over to the snowboarder problem, you'll notice the same thing. There's an 80 on both sides. And so we can divide both sides by 80 and cancel that out. Here's the funny thing about this. This means that number, the 100 or the 80, that was actually the mass of the object. The mass of the object is in both the gravitational potential energy equation and the kinetic energy equation. And so in most of these situations, you're actually going to be able to cancel out the mass, which means that no matter how heavy the roller coaster is, it's actually going to get the same velocity from rolling down that hill. And this is actually really important for roller coasters that is the case, because sometimes you have a roller coaster that's almost empty, like it was the time I went to Legoland the first week that it opened, and it rained the whole week. And so I was the only person riding the roller coaster all day, which sounds great, but was actually kind of boring. Or maybe it's when you go to, a theme park on a normal day, maybe like it's Christmas break and you're at Disneyland and Space Mountain is full of people. Doesn't matter how heavy the roller coaster is, it's actually going to get the same velocity no matter what, because it does cancel out. So that's kind of our first step. Now I'm going to write out my sort of simplified next step. So now I have 10 times 20, which is a really simple solution. Now my next step, now that I've multiplied 10 times 20, is that I'm going to try to get v all by itself. And so the next way to do that is to get rid of the 1/2. In order to get rid of the 1/2, I have to multiply both sides of this equation by 2. All right, now we're getting to the last steps. We have 400 equals v squared. In order to get the v completely by itself, we now have to use a square root. And so now we have the solution to the problem. That roller coaster rolling down that height is going to get a velocity of 20 meters per second. I'm going to fast forward through the steps for the snowboarder problem just for the sake of time. All right, so don't forget, you can slow that down or watch it again if you need to see those steps, if you're really struggling with the algebra. But for the most part, we're not trying to focus on that too much. The basic idea is we're just getting the variable by itself. And so our answer ends up being 5 meters as the height. It's your turn. You're going to try to find the final solution of what is the height that your wrecking ball was released from in order to, you know, reach a velocity of 6 meters per second at the bottom. Good luck with that. Hope you learned something.